Welcome everybody. Thank you for joining our session. So my name is Bram de Kruijf, and there's a presentation from me and Alexander Broekhuis, but because we just have a half an hour, we decided to do single presentations. If you've been to the Remote Services talk yesterday, that was given by Alexander. We work for Luminous Technologies, which is a Dutch IT company. We do consulting, research, and are heavily involved in open source development. So for myself, I'm involved in the Apache ACE provisioning server project and Amdatu platform, which is also Apache licensed stack of web components. Alexander? Should turn that off. Yeah? So how long is that timeout? And I know how to faster transition the slides. Thank you very much. So the talk today is about dynamic hybrid cloud applications, and it's an introduction to the INAETiCS project, which is a research project that has recently started. So let's start with the acronym. You have to have an acronym. And I'm not expecting anybody to remember this after the talk, but it stands for Intelligent Robust Architecture for Time-Critical Systems. And there's a mission statement on the bottom, which is a very long sentence about open collaboration, dynamic services architecture, time-critical systems, broad range of domains, and simple design, irrespective of control strategy. And throughout this talk, I'm going to try and explain what that is about and what we're trying to do. So, just to start with the open collaboration point. INAETiCS is a research project that's being funded by a couple of partners and the European Union. It has been started this year, and it will run for 2.5 years more. And in the end, we hope to deliver what we intend to deliver, and which is what I'm going to talk about today. So. It's an open project, it's a research project. There is a website, and it will be on the last slide. It's inaetics.org, where we present our research findings, and also there will be implementations of the subsystem components in open source in the aforementioned projects, and I'll highlight them again later on. Interesting here maybe is to see that the project is spearheaded by these partners, and there's some big industry partners there. Like Thales, which is in defense industry, they do radar systems, optical systems, and Alliander, which is a big company in the Netherlands doing energy grids, so energy distribution, smart grids, etc., etc. We have the University of Twente with some research department that is specializing in distributed and embedded system security, and some SMB partners, including Luminous, which is my company, PrismTech, which has a brilliant product called OpenSplice, which is an open source implementation of the OMG data distribution services specification, and Security Matters, which is a company that specializes in intrusion detection and security in open infrastructures. So time-critical systems, what do we mean when we say time-critical systems? Well, we mean a lot of systems. But to put it in one sentence, ultra-large online systems that have a critical function and often go across operational domains. So on the right hand, there's a nice image of a cloud, and people who thought cloud applications are just web applications, no, they're not, at least not in our definition. This is a representation of an energy grid, a smart grid. And it kind of shows what we mean with time-critical systems. So basically, there are systems of systems, and there's a lot of subsystems in there that have entirely different characteristics. There may be the operational domain that is actually controlling the energy grid itself and using some kind of SCADA architecture. There may be business domains that are using large databases, big data, profiling, analytics, etc., etc. Customer relation services that have to have access to the CRM data in the system. And on the other hand, you have all kinds of home automation, and now with smart grids, subnets that have to trade with the larger energy grids. And so these are very complex systems, and they are critical. So if you put them in bullet points, we're talking about multiple control strategies. We have SCADA systems, we have processes or subsystems that require real-time requirements on data transfer and operations. But we also talk about functional adaptive systems. The deployment or the functions within the system can change at any time, or should change at any time. Maybe when a subsystem in the grid fails, we need to reroute all the energy distribution in the network, and that's a very critical, time-sensitive process that needs to work. They're technically heterogeneous, well, obviously, because of all these domains, and geographically dispersed. And so this is an energy grid, but in our definition, this is also a cloud. So our partner Thales is doing radar systems. And so if we look at current architecture in combat systems and radar systems for these types of ships, typically they have processing cabinets doing signal processing on the radar imaging that's coming in, and that's located in a couple of cabinets on a particular spot in the boat, and they're doing all the work, and they're oversized in capacity so they can do the processing. But if that piece of hardware fails, there's no more radar. And also here there's a tendency, and there's recently in the US they're building a new warship that just has a data center on board. So that's kind of a private cloud, and even beyond that, integration within the ship, but also across virtual battlefields and communication with control centers, etc., etc. So the INAETiCS project aims to define a unified architecture that can span these domains. Typically in current technology, all these different domains like operational control, like the business domains, they are totally bespoke architectures, different technologies, different architectures, and integration is always a very big problem. We want to define an architecture that can span these domains and provide a solution that has no impedance between them. That will not only allow us to evolve systems more efficiently, but also provide a consistent implementation space and put all these different domains, these subsystems, on a level playing field. Because they are time critical and online systems, we also want to be able to do runtime system evolution, and we also want to be able to adapt depending on context changes. Again, the example of the radar on a warship. The priority of doing signal processing will be very high if there's a missile incoming, and you might want to dedicate more resources to that particular task at that point in time. So dynamically being able to allocate resources at your availability within the virtual private cloud and adapting to those context changes is critical. So in comes the dynamic service architecture, and so this is the OSGi track, and this should be a very familiar picture to anyone familiar with OSGi. But what we think is that the concept of this service whiteboard that we have in an OSGi runtime is also part of the solution to our problem. Using a dynamic service architecture allows us to have different domains with different subsystems that can collaborate in a level playing field. Basically, simply said, we have one big service whiteboard, and all subsystems, independent of domain, of implementation type, etc., can collaborate in this service whiteboard. And what we get from that is that we have published service contracts, we get the service life cycle, allowing us to do all kinds of dealing with dynamics, and also, as shown in the previous presentation, also failure is a form of dynamics. Your service goes away and you have to deal with that. And that fits very nicely. And at the same time, dynamic service architecture, or service architecture in general, doesn't constrain us that much that different domains, different problems can be addressed in different types of ways. So if you need a sequential pattern or event or data-driven pattern, you can still do that and model that and leverage the infrastructure that the services architecture provides you. And if we go to an implementation look at that, well, that provides us also with the capabilities that we're looking for, which is runtime system evolution. We can do semantic versioning, so we can have multiple services where services and or implementations that change over time without breaking their contracts, publishing multiple implementations of services in different versions, all in the same space. We can have modular implementations, so OSGi. We can have bundles, we can have runtime deployments, runtime updates. All of that allows us to do runtime system evolution. Data stewardship, no data coupling between subsystems, again, allows us to do that. And within our practice, we think that OSGi, and because we're also working in other domains, native OSGi provides a very solid implementation technology for us to achieve that. Within our practice, we think that OSGi. So continuous deployment is kind of the main use case that we use for thinking about an INAETiCS architecture and how a system in INAETiCS should work. And what it basically says is that once we deploy an application based on some resources, a cloud of resources, network resources, etc., it should go into a running state, a deployed state, which can be distributed. We don't really care. And two things can happen. Either because of some context change, we need to reconfigure the application's functional behavior, or because something in the infrastructure happens, maybe some hardware fails, a cloud provider fails, or even a positive case, we get extra resources. That also means that we might be willing to change the application and the deployment of the application at that time. But how can we do that? And there we see three types of information that we want to use to do that. And first is the managed requirements. This is basically the configuration of the application. So this can be non-functional, functional properties of the application. It can be quality of service attributes. And if you're talking about a system of systems, there's also the concept of budget and of cost. So this is basically the set of deployment information used to deploy an application. On the bottom end, we have resource capabilities. At any point in time, we have resources in our system, and they have specific capabilities. So it might be a generic cloud compute node that can do all kinds of things. It's kind of generic. And it might be running an OSGi container, and we can provision software components there. Or it might be a highly specialized piece of software, or like a GPU, or something that's very good at signal processing. And it needs to be able to say, well, I'm participating in your system, I have this capability with a certain quality of service and a possible cost. So these are kind of, well, they're not static, but these are two sets of information that come from deployment and the resources in our system. But that's not enough in itself. So the third part is runtime metrics. So we want the system to be monitoring our applications deployed into the system at any time. And that could be as simple as monitoring resource utilization, but it could also be very application-specific monitoring of particular performance metrics, like how long does it take me to generate a certain set of information on average, and it shouldn't be above or below 10 milliseconds. So to be able to take these three sets of information and to make that into a working system, we come up with a kind of layering in our services architecture, which at the core provides us with basically three layers. So there's application services, and that can be any kind of, any type of application. We don't say too much about what types of application frameworks should be used there. Also because we want to be applicable in many domains. So the application architecture is, okay, we know it's there, and basically the function of the INAETiCS system is to be able to deploy that in its most optimal way. And to do so, we need that system. On the bottom end, same for networks and resources. It can be basically anything, and we want to abstract from that. And that's what provides us with three conceptual layers in the architecture, which are the coordination services. Coordination services look at the entire system and perform tasks. So like the application deployment use case, that's a coordination service. Container services are the sets of components and services that support applications in their deployment. So if you have an OSGi application or OSGi bundles that form a subsystem of that application, then we need to be supported by the container services. So for one, it needs to have a container, but it also might require DS or some other form, maybe a log service or anything that is needed in the environment to support the application component from running successfully. And at the bottom end, we have something that we call fabric services, which are basically the abstraction from the network and the resources, and provide the bottom, the grid, the network that the infrastructure of the system is running on. So I'll zoom into those a little bit more. Did I? So fabric layer. Basically, we want to abstract away from our resources. The way we do that is by providing a peer-to-peer network of resources that participate in any system. Any resource in the system is represented by a node. We partition them into zones for efficiency reasons, but also for being able to bridge domain and technology boundaries. We provide some basic functionality in there, like coordination, making sure that specific functions are being executed within the distributed system in a reliable manner. And it provides a basic messaging and relaying infrastructure that allows the nodes to communicate at a very basic level. So again, in the layering, these nodes represent an abstraction from a resource in the system, and they have a couple of responsibilities, and mostly providing the system with information about their capabilities. So again, that's functional requirements, maybe functional endpoints. So if it's a static node, or if a node that runs on a very specialized hardware resource, it may directly provide a functional endpoint. But if it's like an OSGi framework that's able to host containers or host OSGi bundles, it may have functional endpoints that says, well, if you want to provision me with some kind of software component, here I am. So basically in implementation, this is a very basic grid or peer-to-peer network of nodes that represent the resources in the system. And we're working on some polyglot implementations. Again, because we want to cross domains and technology boundaries, this should be a minimal set of functions that such a node agent should be required to perform. And anything above that, it can announce through, okay, these are my capabilities. And so they are being implemented within the Amdatu platform project, which is based on OSGi, Java OSGi, but we're also aiming to do an implementation in the Apache Helix project, which is an Apache incubator project that does a native implementation of OSGi. There's been a couple of talks about that already at this conference. And finally, they also could be entirely custom and embedded, or embedded. So the core services in that would be, we need to have discovery, we need to have trust amongst the nodes. We need some strategies to maintain topology, depending on how large the system is, do messaging, do some coordination tasks, have some form of initial provisioning in some cases, is like also an optional capability. And on top of that, we provide a layer of remote services. Again, there's been a couple of talks about remote services already. And as Tim showed in a previous presentation, it's a very nice way to abstract away from the actual physical deployment topology of the system. The remote services provides any components that are provisioned onto such a node agent to access Fabric services directly through the local service registry if it's running an OSGi runtime. So that's our case, but without having to know where those the actual providers of those systems are, or of those services are. So that's the foundation, and on top of that we build a component layer. Or the container layer. And again, the responsibility of the container layer is to provide the runtime for application components. And to be able to do that, the implementations we're working on are OSGi runtimes. And to support that, we need some form of provisioning, which means that if the system decides that a certain software component should run on a specific node, we need to be able to provide that node with the software artifacts and configuration artifacts that it needs to perform its function. We need to provide it with an application context. So if an application is distributed across multiple containers, it doesn't know anything about the location or the deployment topology, but it just knows I want to talk to service A. We have to provide it with the context, the SOP context, and through the OSGi service registry to be able to talk to service A. There might be a host of supporting services, including logging, QoS monitoring, etc., etc. The container adds a layer on top of the fabric, and in that sense also adds capabilities into the system. So again, these can be non-functional and functional capabilities of the specific container implementation. They can add endpoints, extending the node capabilities. And as an important example for us is the capability to do multi-tenant deployment of components in the OSGi runtime. So how are we doing that? Provisioning, we're using the Apache ACE project. It's an OSGi software provisioning framework that uses deployment admin specification from the OSGi spec to be able to do fine-grained software updates to OSGi runtimes. We're using some components from the Amdatu project to do application context, so service visibility, on-demand services. Again, if you think back about the energy grid and everything is going to be a service in a big service whiteboard, you don't want that all in your local service registry. So conceptually there's one big service registry, but depending on what type of application is running, in what form of configuration, etc., it will only see the relevant set of services. Also, if you think in a multi-tenant context, data service A or tenant A will have a data service that's logically different than the data service for tenant B. So that's all managed through service visibility and some components like Amdatu multi-tenancy that provide that. And finally, there's going to be a set of dynamic services, and actually all services at the container layer are dynamic. But these are the supporting services that are required for the system to function in its current deployment topology. So for example, if an application is made up out of two components that are deployed in one runtime, they can just communicate in VM But if they are scaled out and running on different nodes, they might need some networking service to be able to do the ad hoc connections. If they choose not to use the messaging layer because they have, like in the time critical domain, real-time guarantees, we need to be able to do ad hoc services. So networking, security, etc. So and finally, on top of the coordination layer, which is all about managing this INAETiCS system and managing the applications deployed in there. So the typical services provided at the coordination layer are the application deployment, that continuous loop that deploys, evaluates, and reconfigures applications to meet their QoS requirements as best as possible. Same goes for resource management. If we're running on a fixed architecture or fixed set of resources, we may not be able to do that much. We might optimize message routing and stuff like that. But if we run in a cloud environment, we might decide that, well, we're not meeting our quality of service requirements. Let's scale up and get some more EC2 nodes. Network management, again, ad hoc connections and security. Also, cross-cutting concerns that go over the entire systems. And finally, in addition, because all container application components running in containers are like scoped to the local runtime, but applications may want and need to scale out, the coordination layer will also provide a set of utility functions that's provided to applications that choose to use them to be able to coordinate distributed operations across the deployment. And that could be priority-based scheduling or load balancing, stuff like that. So again, these coordination services are logically single entities, but they're also in implementation distributed across the INAETiCS fabric. And what they do is, for application deployment, exactly matching these requirements and capabilities, doing the QoS monitoring, and taking the actions to ensure that the deployed applications perform as good as possible. Again, like in real-time domains, there's always the question about what real-time is, and we try to come up with a system that will degrade gracefully, right? So we will do our best to optimize the deployment, optimize the network, and meet QoS requirements. If that doesn't work, okay, we're going to degrade gracefully. For resource management, we're currently looking at Apache JClouds, OpenStack, OpenControl, what is like a software-defined networking technology that allows us to dynamically reconfigure networks and resources, and also provide us with isolation and multi-tenancy at the network layer. So in an overview, the system and the layering works like this. And on the left hand, you see the functional requirements going down, the capabilities coming up, the nodes in the fabric providing capabilities, containers adding capabilities to that. And that set goes into the coordination services. On the right hand, also runtime, QoS, and functional reporting added to that mix. And based on that, we try to come up with a optimal deployment topology, which will be re-evaluated over time whenever either requirements change, metrics show us that we're not meeting our QoS requirements, or our capabilities from the network layer or the resource layer change. So in conclusion, what we're trying to tell you here is that INAETiCS is a dynamic service architecture, and its main focus at this time is to provide that a consistent design space that allows us to do implementations on conceptual or do implementations within such a single design space across the different domains and technologies. We want to be able to implement that into a dynamic runtime that actually supports dynamically deploying these applications and dynamically managing the network and having this kind of continuous evaluation loop that will react to any changes in the context, keeping systems going and trying to meet the desired quality of service as best as possible. And implementation at this point being conducted at several open source projects, including the Amdatu platform and Apache Celix. And we're still working on that, under construction. So that's all I have for now. Only thing I would want to point out to you, if you want to know more about the OSGi provisioning and more on a technical level on how that works with Apache ACE, there's a talk tomorrow also in this room that gives you more technical information on how that works. So if there are any questions. No questions. Not that clear.
Thank you, Ryan.
Thank you.